Hello and welcome to the problem-solving session on creating magnetic fields. One theme that emerged when we worked out these problems in the in-person class session was that this is one where it really pays off to stay symbolic as long as possible in your solutions because it greatly cuts down on the amount of work that you have to do in solving these particular problems. Question 1 reads, in the figure, two long straight wires are perpendicular to the page and separated by a distance D1 equals 0.75 centimeters. Wire 1 carries 6.5 amps into the page. So what are the magnitude and direction of the current in wire 2 if the net magnetic field due to the two currents is 0 at point P, located a distance here 1.5 centimeters from wire 2? Well, let's solve the magnitude piece first, I suppose, since that's the order they put it in. We want the magnitude of the magnetic field from wire 1 to equal the magnetic field from wire 2 if they're going to sum to be 0. And that means mu 0 times I1 over 2 pi, in this case it would be, I'm just going to call it R1 right now, has to equal mu 0 I2 over 2 pi R2. And so this is where, again, keeping things symbolic before actually calculating a magnetic field can be helpful, because you'll notice mu 0 is going to cancel, 2 pi is going to cancel, and we're going to be left with an expression for I2 is R2 over R1 times I1. And in fact, R2 and R1, we can work it out. R2 is this D2, it's the 1.5 centimeters. And R1 is the 1.5 centimeters plus 0.75 centimeters. So this ratio is actually just going to be 2/3, since D2 is twice what D1 is. You could write it out again as 1.5 centimeters over 2.25 centimeters, but that reduces to 2/3, 2/3 of I1, and so 2/3 of 6.5 amps is 4.33 amps of current. What does the direction of the magnetic field, well, what does the direction of the current need to be? Well, if you are at point P right here, whoops, P, not B, and you get a magnetic field from wire 1, well, wire 1, the current's going down into the page, so if I orient my thumb down into the page, my fingers curl around in a clockwise direction, so that means down here at point P, below where wire 1 is, the magnetic field from wire 1 points to the left. And that means to cancel out, I need the magnetic field from wire 2 to point to the right. And again, using that same idea, because wire 2 is above the point, if I point my thumb up out of the page, my fingers curl around in a counterclockwise direction, which at point P directly below would produce a magnetic field to the right. That means that the direction of the current in wire 2 is out of the page. Second problem uses a similar concept. In the figure, we have two long straight wires. They're separated by 16 centimeters, and they carry currents. I1 is 3.61 milliamps. I2 is 3 times I1. So whatever 3 times 3.61 works out to be, turns out we're not going to need to calculate it. Out of the page, where on the x-axis is the net magnetic field equal to 0? So I'm going to just sketch this a little bit larger so I can fit my hand in the picture, or at least attempt to. So I got I1 and I2, and they're separated by some distance d. Well, if I put my thumb, again, in the direction that current's coming in the wire out, my fingers curl around like this. To the right of wire 1, I get a magnetic field that's up. And if I do the same over at wire 2, to the left of wire 2, I get a magnetic field that is down. So the net magnetic field is going to equal 0 somewhere in this region in between them. And because wire 2 has more current than wire 1, that location's got to be somewhere closer to wire 1 than it is to wire 2. At that location, we'll have the magnetic field from wire 2 pointing down, and the magnetic field from wire 1 pointing up. We want to know more specifically what that position is, so I'm just going to go ahead and call this distance x, and that would make this distance, the distance I am from wire 2, d minus x. Alright, so I need, again, magnetic field from wire 1 to equal the magnetic field from wire 2. If we write that out symbolically, that's mu 0 times I1 over 2 pi, and then this distance will be x. That's got to equal mu 0 I2 over 2 pi, and that distance is d minus x, the distance that wire 2 is away from this spot. But I2 is equal to 3 times I1, so I'm actually going to rewrite this as mu 0 times 3 I1 over 2 pi times d minus x, and then many things cancel out if I look at these first and third items in my equality. Mu 0 goes away, 2 pi goes away, and even I1 goes away, and that's going to help us answer question B. So we could rewrite this as 1 over x equals 3 over d minus x. If we solve that, I get 3x equals d minus x. That gives me 4x equals d, or x equals 1/4 d, which, since d is 16 centimeters, must be 4 centimeters along the x-axis to this location. Part B says, if the two currents are doubled, does the 0 point shift towards wire 1, shift towards wire 2, or is it unchanged? Well, again, as we showed here, the ending answer only depended on the ratio of those currents. And if I say double I1, I will also double I2, and that will keep everything the same in the ratio. I'll end up at the exact same position. So the answer to B is that it remains unchanged. Questions 3 and 4 brought in the concept of circular loops. And in this circular loop problem, it reads, in the figure, part of a long insulated wire carrying a current of 5.78 milliamps is bent into a circular section of radius r equals 1.89 centimeters. What's the magnetic field at the center of curvature C if the circular section lies in the plane of the page as shown? And what about if it is perpendicular to the plane of the page after being rotated by 90 degrees counterclockwise as indicated? I don't know if this is something you can visualize. Sometimes I think that half the battle in solving these electromagnetism problems is being able to visualize things three-dimensionally, which can be tricky. But basically we have a straight wire. We've bent one piece of the wire into a loop, and so the very first problem, things are aligned in this way. When it talks about rotating at 90 degrees clockwise, you keep the wire flat like this, but you take this loop and you turn the loop sideways so that now, hard to do with these wires, the loop is oriented in this direction. See if I can get my hand out of at least much of the picture. All right, so let's go ahead and see how we might do this. This is really a superposition of two things. So in part A, when they're both lined up, it's like taking a straight wire and finding the magnetic field at point P, plus taking a loop of wire and finding the magnetic field at point P. So the magnetic field from a straight wire is mu 0 I over 2 pi times the distance that we are away. The magnetic field from a loop is mu 0 I over 2 times the radius of the loop, but the distance we are from the straight wire is the same as the radius of the loop. So these r's are going to be the same in this particular situation. So the net magnetic field is mu 0 I over 2 pi r plus mu 0 I over 2r. As shown, the direction of the current in the straight wire is to the right. So if I curl my fingers around it, above the wire, they're coming out of the page. And in this loop, same kind of thing. If I go up the right side of the loop, this is the direction of the current. Inside the loop, my fingers are coming out of the page. I go over to the other side of the loop, which is super hard to do on camera. Current's going down. My fingers are coming out of the page in the center of the loop. So both of these are going to produce magnetic fields at point P that are out of the page in this situation. So this is my expression, but these r's are the same, so I can really write this as mu 0 I over 2r times 1 over pi from the first term plus 1 from the second term. And then we'll go ahead and plug in a bunch of numbers. This is, let's see, mu 0 is 4 pi times 10 to the negative 7 Tesla meters per ampere. The current, we're told, is 5.78 milliamps, so 5.78 times 10 to the minus 3 amps. And 2 is there. The radius is 1.89 centimeters, so 1.89 times 10 to the minus 2 meters. And then we have this 1 over pi plus 1 term out there. If you punched all that into a calculator, you get 2.54 times 10 to the negative 7 Teslas. And the direction of that, if to the right is the x direction and y is up, the z-axis comes out of the page. So the direction is in the positive z direction. Part B gets a little bit trickier because, again, if we rotate that loop as we were talking about, the magnetic fields no longer point in the same direction as each other. And in fact, I think I'm going to try to draw a top-down view of this, and I don't know if that's going to make sense or not, but if I do a top-down view in this orientation, the straight wire goes this way along the z direction, or the x direction again, just like it was initially. But this loop has turned 90 degrees, so now I'm looking down on the top of the loop, and that means the magnetic field here at point P, which is in the center, is going to come, well, the magnetic field from the straight wire is going to be down. The magnetic field from the loop is going to be pointing to the right. And this means that the overall magnetic field from this whole system points down and to the right. So there's the net magnetic field. Okay, so can't quite get this line in here because we need to now sum these in this fashion, but it is true that B net squared equals B wire squared plus B loop squared. That's just applying our Pythagorean theorem. So that means that the net magnetic field is actually the square root of, let's see, B wire squared. So this one is B wire here. Mu 0 I over 2 pi r. Square that all. And then the loop, square that all. Mu 0 I over 2 r all squared. Again, those r's are the same. And if you square all this stuff, you can actually pull that term out of the square root. I could rewrite this as mu 0 I over 2r. And the stuff that stays in the square root is 1 over pi squared and 1 squared. If you put all the numbers in that expression like we did up top, the only thing that changes is this multiplier at the end. It's now square root of 1 over pi squared plus 1 squared rather than the 1 over pi plus 1 we had. Then the magnitude of the net magnetic field is now 2.02 times 10 to the negative 7 Teslas, and we would expect it to be less because these two vectors are not pointing all in the same direction anymore. What is now the direction of the magnetic field? Well, this is the x direction. Z comes out of the page, but if I'm looking in this top down, Z is coming now down to the bottom of the page. So it's in the XZ plane here, but what's one of these angles? Well, I'm just going to pick this angle as theta. If I do that, then let's go tangent. The tangent of theta is equal to the opposite over the adjacent. So here's the opposite side of the triangle. If I moved B wire over here, oops, I'm sorry, B wire would be the opposite side of the triangle. B loop is the adjacent side of the triangle. So the opposite would be B wire. That's mu 0 I over 2 pi r. The adjacent side is B loop. That's mu 0 I over 2r. And again, lots of stuff cancels. Mu 0 gone, I gone, 2 gone, r gone, and I'm left with 1 over pi over 1 over 1, which probably makes more sense to just write as 1 over pi. So if I say the tangent of theta is 1 over pi, then theta is the inverse tan of 1 over pi. Pull out a calculator and see what that ends up being. Inverse tangent of pi to the power of negative 1 gives me 17.7 degrees. So the magnitude would be 2.02 times 10 to the negative 7 Teslas, and the direction would be 17.7 degrees off of the x-axis in the xz plane towards the positive z-axis, which is just a little awkward to represent. Another loop problem, but one that will involve fewer calculations, is number 4. A straight conductor carrying a current of 5 amps splits into identical semicircular arcs as shown. What is the magnetic field at the center C of the resulting loop? So I'm going to draw this a little bit bigger and label some stuff. So here's one place where we need to bring an idea forward from our circuits unit, and namely what happens to the current when it gets to a junction. So right now I've got 5 amps of current that goes here. When it gets to this junction, assuming these are identical loops, 2.5 amps would go this way, 2.5 amps would go this way, and they would recombine over here to form a 5 amp current. What is the magnetic field at the center C of the resulting circular loop? Well, I need to use my right hand rule a couple of times. The current that goes over the top, if I align my thumb in the direction of that, then I curl my fingers around. They're going into the page in the region below that wire. So the magnetic field below that wire would look like this. Above the wire, we would draw vectors for out of the page. Same kind of thing, the lower wire, the current goes this way, so above that wire, the magnetic field's coming toward me. So I'd get this, and outside I'd get this. But we want to think about the very center of the loop. Well, at the very center of the loop, the magnetic field from the top part of the wire is into the page. The magnetic field from the lower part of the wire is out of the page. And because magnetic field is proportional to both current and distance, if there's the same current going in both wires and I'm the same distance from both of those wires, the net magnetic field at C is going to be 0. Problem number 5 reads, a figure shows wire 1 in cross section. The wire is long and straight, carries a current of 4 milliamps out of the page, and it's a distance D1 of 2.4 centimeters from the surface. Wire 2, which is parallel to wire 1 and also long, is at a horizontal distance D2 is 5 centimeters from wire 1 and carries a current of 6.8 milliamps into the page. What is the X component of the magnetic force per unit length on wire 2 to wire 1? Lots to try to dissect there. I'm going to sketch a slightly larger axis so I can mark it up with a bunch of stuff. So here is wire 1 carrying current 1, and down here is wire 2 carrying current 2, and they're in different directions here. All right, so the logic goes like this. Wire 1 produces a magnetic field around itself, and if I orient my thumb in the direction that current's flowing out of the page, my hand curls around in a counterclockwise direction. So that means wire 1 is producing a magnetic field that is around itself like that. Well, if I trace that over to this point, that means the magnetic field at this location from wire 1 points up and to the right. So that's the magnetic field from wire 1. And you can approach this a couple of different ways. I think it's slightly easier to break the magnetic field right now into X and Y components. So I'm going to go ahead and do that. Here is the magnetic field from wire 1's X component. And here is the magnetic field from wire 1's Y component. So this is the piece that's the new piece of this, that a current carrying wire produces a magnetic field. Now we have to jump back to the idea that we previously had, which is that if I have another current carrying wire sitting in that magnetic field from wire 1, wire 2 is going to feel a force due to that magnetic field. That's our force on a moving charge idea that began the chapter. So here, if I orient my index finger in the direction that the current is flowing, which is into the page, and then I get my other fingers to be aligned with the direction of the magnetic field, that leaves my thumb pointing down and to the right. Again, it's going to be in a direction perpendicular to the direction of both the current and the magnetic field. So this is the direction of the force that wire 1 puts on wire 2. But it also has X and Y components. And one way you can think of this is that the X component of this force is produced by the Y component of this magnetic field. And the y component of the force is produced by the x component of the magnetic field. Since the problem is only asking me what is the x component of the magnetic force per unit length here, that's the only one that we need to focus on, which means the y component of the magnetic field is what we need to focus on as well. All right, so lots of information in there to digest, but we'll go ahead and try to work this out. So the first step, calculation-wise, would be to figure out what the magnetic field from wire 1 is right here. Well, magnetic field from any straight current-carrying wire is mu 0 I over 2 pi times R. And let's see, that is, let's personalize that a bit. That's mu 0 I1 2 pi. And again, I'm going to try to leave this symbolic in hopes that things will cancel out for me. This distance right here, if this is d2 and this is d1, the distance here, if I use Pythagorean theorem, must be the square root of d1 squared plus d2 squared. So that's the full magnitude of the magnetic field here at this location. I only need to know the y component of it because that's the one that's producing the x component of the force. So the y component is going to be the full magnetic field times the cosine of this angle right here. Well, the cosine of that angle is the same as the cosine of, or the angle here rather is the same as the angle on this triangle in my setup. And the cosine of this angle would be the adjacent side, which is here, which is d2, over the hypotenuse, which is the square root of d1 squared plus d2 squared. So the y component of this is the full magnetic field times the cosine of theta. Or I could write that as the full magnetic field times d2 over square root of d1 squared plus d2 squared. So I got my y component of my magnetic field, and now I'm jumping back to force on a current carrying wire concepts. The force on a current carrying wire is the current I, the length of the wire L, and the magnetic field which is producing that force B times the sine of the angle between the direction of current flow and the direction of the magnetic field. Well, the current flows into the page, the magnetic field is up at an angle, those are 90 degrees from each other, so the sine of theta is just 1 in this particular case, as it is in many cases of the problems that we look at. And so the force that wire 1 puts on wire 2 is going to equal the current flowing in wire 2, so that's I2, times the length. Well, I don't know the length, and in fact, this asks me for magnetic force per unit length. So let's go ahead and move length over to the other side and get force per unit length. Times the magnetic field. Well, the magnetic field is this thing right here, the y component. So that's going to be mu 0 I over 2 pi, and then I'm going to give a square root of d1 squared plus d2 squared here, but I'm going to multiply that by this expression for the cosine of the angle, so I'm going to end up with a d2 over d1 squared plus d2 squared, and that will give me my full force per unit length. There's nothing that really cancels in this one, except when I write out mu 0, part of that cancels with the 2 pi. So I2 is 6.8 milliamps, so 6.8 times 10 to the minus 3 amps. Mu 0 is 4 pi times 10 to the negative 7 Tesla meters per ampere. I1 is 4 milliamps. D2 is 5 centimeters, so 5 times 10 to the minus 3 meters. And that all goes over 2 pi. And then here I've got 2.4 centimeters, converting to meters squared, plus 5 centimeters, again converting to meters squared. And there we go. Punch all that into a calculator, and I come out with the force per length being 8.84 times 10 to the minus 11 newtons per meter. The final problem that we solved in this set of practice problems reads, in the figure, 5 long parallel wires in an XY plane are separated by a distance d equals 8 centimeters. They all have lengths of 10 meters, and they carry identical currents of 3 amps out of the page. Each wire experiences a magnetic force due to the currents in the other wires. What is the net magnetic force, magnitude, and direction on wire 1, wire 2, wire 3, wire 4, and wire 5? At first blush, this looks like we got to do a lot of calculating, but it's not going to be as bad as you might think from first glance. So again, if all the currents are coming out of the page, let's focus on wire 1. So here's wire 1, and it's got current coming out of the page. That current's going to feel a force due to the magnetic fields from all the other wires. And if all the other wires have current coming out of the page, over on their left-hand side, if you use the field right-hand rule, the fingers on your right hand are pointing down to the bottom of the page, which means that I'll get a magnetic field from wire 2 that's down. I'll get a magnetic field from wire 3 that's down, but it's smaller because it's further away. 4 is even smaller. 5 is smallest yet, but the overall magnetic field at this location is downward due to the current in all of the other wires. If I then apply my force right-hand rule, I got current coming out of the page. Look, see if I can do this. Current coming out of the page. My magnetic field is down toward the bottom of the page, and that leaves my thumb pointing to the right. That means the force on current carrying wire 1 due to all the other wires is pointing to the right. All right, how big is that force? Well, force is ILB sine theta. Current's coming out of the page, magnetic field is down, those are 90 degrees apart. The current is the current in wire 1. The length is the given length, and the magnetic field now is where I have to bring in my expression for magnetic field from a current carrying wire. So that's going to be mu 0, and I'm going to have I2 over 2 pi, and then that distance away is going to be d. I'm going to have a contribution from wire 3, and that's 2 pi, and the distance is 2d. Wire 4, mu 0 I4 over 2 pi, the distance is 3d. And wire 5, mu 0 I5, 2 pi, and the distance is 4d. Now, this would be a super ugly problem if those currents were different or if those distances were different, but they're not, and we can take advantage of that. All these i's are the same. So really, I can factor an I out of here, and this expression simplifies to I squared times the length times mu 0, that's everything in the numerator, over, I can pull a 2 pi and a d out of the denominator, and then I'm left with 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. And we can go ahead and plug in numbers. So the current is 3 amps, that's squared, The length is 10 meters. Mu 0 is 4 pi times 10 to the negative 7 Tesla meters per ampere. 2 is 2. The distance is 8 centimeters. So 8 times 10 to the negative 2 meters. Pi is pi. And then common denominator here is 12. So if you add 12 twelfths and 6 twelfths and 4 twelfths and 3 twelfths, you end up with 25 twelfths. And that number ends up being 4.69 times 10 to the negative 4 newtons. And the magnetic force is to the right, as we previously reasoned. All right, how about wire 2? Also, here's wire 2. Wire 2 now is to the right of wire 1, so wire 1 produces a magnetic field that is up here. There's B1. Wire 3 produces a magnetic field that's down, but 3 and 1 are the same distance from 2, so that's down, from 3. 4 is further away, but going to be down. 5 is further away, also going to be down. But notice that 3 and 1 are equal and opposite in magnitude, equal in magnitude and opposite in direction. So they essentially cancel out of the overall picture, and the net magnetic field is due only to wire 4, which is a distance 2d away, and wire 5, which is a distance 3d away. So the force expression is pretty similar. I'm going to end up with an expression like this, except I'm only going to have something 2d away and something 3d away in my expression. So I'm going to end up with an I squared L mu 0 over 2d, 2 pi, I'll put the d over there. And then it's going to be 1 over 2d, so that 1 over 2 stayed, 1 over 3d, 1 over 3 stayed. Everything else is gone, and if you plug numbers into there, very similar to what we just did, you find this is 1.875 times 10 to the negative 4 newtons. It's also going to be to the right because the net magnetic field is down. And now we should be able to pick off the rest of the answers by inspection. If we think about wire 3, wire 3 is going to feel a magnetic field from wire 1 that's up, from wire 2 that is up, from wire 3 that is, or wire 4 rather, that is down and equal to wire 2, and wire 5 that is down and equal to wire 1. And so all those magnetic fields add up to a net magnetic field that is 0, which means the force on wire 3 is 0. Wire 4 is the same situation as wire 2, except you'd flip everything over in this picture, which means the force is the same as it was on wire 2, but the magnitude, or the direction rather, is to the left. And wire 5 is the same magnitude as the force on wire 1, but the direction is also to the left. So the net effect would be all of these wires would pull in towards the center of this arrangement. So those are the problems we looked at in the Creating Magnetic Fields problem-solving session. As always, if you happen to notice an error in the calculations or the solutions, I'd appreciate you letting me know about that. Thank you.